Okay, let's talk about something we use literally every single second of the day, but probably never really think about. Numbers. Now, I promise this isn't going to be some dry math lesson. Nope. This is an adventure story. It's a tale of human ingenuity, of really tough problems, and the absolutely brilliant solutions that, well, built our entire world. So let's dive in.
No, seriously, have you ever just stopped and wondered about that? I mean, we've got our 10 digits, 0 through 9, and then poof, we just start all over again at 10. Why 10? Is it just because we have 10 fingers? I mean, that makes some sense, right? But is that really the only way to do it? Or, and here's the kicker, is it even the best way? You see, our whole base 10 system feels so natural, like it's a law of physics or something. But it's not. It's a total invention, a tool that we humans came up with. And to really truly appreciate how genius it is, we've got to go back in time and look at the problems it was actually built to solve.
All right, let's start at the very, very beginning. I'm talking, forget calculus, forget algebra, forget all that stuff. The first ever problem was way simpler. It was basically, hey, you've got some sheep, I've got some grain. How in the world do we keep track of it all?
And the first answer was probably the most obvious one you could think of. For every one sheep, you make one little scratch on a bone or a piece of wood. Simple, right? One mark for one thing. It's direct, it's easy, and for a little while, yeah, it worked perfectly. But what happens when you don't have just a few sheep? What if you have 100 or 1,000? All of a sudden, that simple little system turns into a total nightmare. Just counting all those marks is a pain, it takes up a ridiculous amount of space, and oh my gosh, forget trying to do any kind of math with them. Add or subtract? No way. It was clear, humanity needed a better way. So the next big idea was basically a shortcut. People started thinking, hey, instead of a bunch of individual marks, let's just create special symbols for groups of things. And this is what led to systems like the Egyptian numerals and the one we all know, Roman numerals. But here's the thing. While this definitely solved one problem, it ended up creating a whole new one, a much, much bigger one. The basic idea was pretty smart, right? Instead of drawing 5 little lines, just write V. For 10, you write X. For 100, C. Boom. It totally solved the too many marks problem and, for sure, was a huge leap forward in efficiency. But, and it's a big but, this new system created a massive new headache. Just try doing math with it. I mean, look at that. How would you even begin to add MDCTLXX to CMXLI? You'd have to what? Mentally unpack all those letters, try to regroup them somehow, and then put it all back together into a new set of letters? It's just so clumsy. It's a terrible system for actually doing anything. And this just shows you the problem perfectly. On one hand, you've got this jumble of letters. On the other, 1776 plus 944. It's just so clean, so organized, and so much easier to solve. Look, Roman numerals were fine for carving a date on a building, sure, but for doing any real math, they were absolutely terrible.
Okay, so this brings us to what is without a doubt the single greatest breakthrough in the entire history of numbers. This was an idea so powerful it literally changed everything. It came to us from ancient India, was refined by brilliant Arab mathematicians, and it's all about two things: the power of place and the invention of, well, nothing.
This right here, this is the magic key. Think about it. In our system, the number 2 doesn't just mean 2, not always. In the number 25, that 2 means 20. In 250, it means 200. The symbol itself, the 2, is exactly the same, but its position, where you put it, gives it a completely different value. This, my friends, was the absolute game changer.
But there was a catch, a big one. For this whole positional system to work, you absolutely need a way to show that a position is empty, right? Like, how do you write the number 205? You've got a 2 in the hundreds place, a 5 in the ones place, but what do you put in the middle, in that empty tens place? You need a placeholder. You need a hero. You need the number 0. Let's just break this down with the number 205. That 5 on the end, that means 5 ones. Simple. The 2 at the front, that means 2 hundreds. But that beautiful, elegant 0 right in the middle, it's doing the most important job of all. It's holding the tens place open, making sure that 2 stays in the hundreds column where it belongs. This is the key that unlocks easy math. It's what allows for those simple, repeatable steps, algorithms like carrying the 1, that make calculation possible for everybody. Seriously, without 0, the whole system just falls apart. So this Hindu-Arabic system, with its brilliant positional notation and the hero 0, it seems pretty perfect, right? And for us humans, yeah, it pretty much is. But then the 20th century rolls around and a brand new problem shows up. How on earth do we get machines to count?
See, a computer's brain isn't like ours. At its most basic, fundamental level, a computer is just a giant collection of switches. And a switch can only be one of two things. It's either on or it's off. That's it. There's no kinda on or a little bit off. So here's the puzzle. How do you represent 10 different digits, 0 all the way up to 9, when you've only got 2 states to work with?
Well, the solution was just elegant. Instead of trying to teach a machine 10 different symbols, the pioneers of computing created a system that only uses 2, a 1 for on and a 0 for off. We call this base 2, or binary. And what's so amazing, what's so cool about this, is that it's built on the exact same revolutionary idea of positional notation we just talked about. So, think of it this way. In our everyday base 10 system, the places are ones, then tens, then hundreds, and so on. Well, in binary, the places are ones, then twos, then fours, then eights, and it just keeps doubling. So a number like our 5 becomes 1 4, 0 2s, and 1 1, which we write as 101. It's the same powerful concept of place value, just adapted for a machine that, you could say, only has 2 fingers. So look how far we've come. We've gone from simple scratches on a bone, all the way to the fundamental language of our entire digital world. Every single step along the way was driven by a new problem that forced us to come up with an even more clever, more abstract solution. And all this, it brings us to one final, kind of philosophical thought. I mean, you can really see the evolution. We started with those simple but clumsy tally marks. Then we moved to the slightly better but still terrible for math, Roman numerals. Then came the real revolution, the Hindu-Arabic system with position and 0. And finally, that same idea was adapted into the binary that powers every computer on the planet. Every step was a brilliant solution to a really tough problem.
And when you boil it all down, that's what this whole story is really about. It's not just about math homework, right? It's about the incredible power of the human mind, our ability to create these amazing abstract tools to better understand and even control the world around us.
So, I'll leave you with this one last thought to chew on. We clearly invented all these different systems, right? Tally marks, Roman numerals, binary, those are human creations. But what about the rules underneath it all? Was the very idea of the number 3 just floating out there in the universe waiting for us to find it? Is math something we create from scratch, or is it a fundamental language of the universe that we are just slowly, brilliantly discovering? Something to think about.